Okay, so good evening everyone. Uh, Today we'll be discussing about the reciprocal lattice, Wigner seed cell, and these are the topics which the professor has discussed in the last week. And it is building upon the concepts that we have developed in the last week about the reciprocal spaces. So what we had done in the last class was what we had done in the last class was the reciprocal space, and or we can call it the K space, and it has the dimension of 1 by L, the inverse length dimension. Okay, and so in real space, if we have a simple cubic structure, in reciprocal space it will be also a simple cubic. In real space, if we have FCC, then in reciprocal space we would have BCC, and if in real space we have BCC, then in reciprocal space we will have FCC. So this reciprocal space is just an equivalent representation of the uh, real space. But why do we go and make our life so complicated by taking this reciprocal space? Because it gives some
In simple
information.
cubic, it is simple cubic. In simple cubic, it is simple cubic.
Yeah, exactly.
Reciprocal,
Yeah,
yeah.
yeah. So the point of going to, so what is the point to go to the reciprocal space? So it is just that we want to understand, because the reciprocal space gives the information about the interactions of material with a particular probe. That probe can be light or some ion beam, or like for example some neutron beam, so anything it can be. And we will today talk about something called Wigner seed cell. So what is this? It is defined as a region in the space. So what we have is, we talked about different lattices. Lattice means it is the collection of points which can be it is a periodic collection of points. So given a periodic collection of points or a lattice, it is that region in space that is closest to a given lattice point than to any other lattice point. So for example, if you have a lattice, you choose one point, and that region in the space which is which is nearer to that particular point than any other point, it is the uh, it is the Wigner seed cell for that particular point. So let us see how. So this is the definition. It is the suppose if we have a lattice, we are taking an example of a two-dimensional lattice, and we are saying that these are the points. So these blue circles, these are your lattice points. Now we are choosing a particular point. Let's say this is a point, and that region in the space which is closer to this point than to any other point is your Wigner seed cell. That region is called the Wigner seed cell. Okay, so I hope this concept is clear. So now how do we know that what is the region in space which is closer to this point? So what we do, we take this point as an origin, then we join this point with other lattice points. So we are joining this with here, joining this with this point, joining this with this point, joining this with this point, with all the other points we are just joining it. Now what is happening? Now we want to find what is the, now let us take these 2 points, this point and this point. So what is the region in space which is closer to this point than to this point? It is the region, like you take a perpendicular bisector to the line joining these 2 points, and the region which is on this side, that is that region which is closer to this point, right? Similarly, you take the perpendicular bisector to the lines joining all the other points, and the region which is enclosed by these perpendicular bisectors. So this green line, if you see, these are your perpendicular bisectors, and the region enclosed by these perpendicular bisectors is your Wigner seed cell, or that is the region which is closest to the given lattice point. In this case, this lattice point. This point is clear, no?
Yeah. Yep.
Yeah. Okay. Now, so let us look for a different lattice. So this was the example of a square lattice, right? Now we are taking a different lattice. It is a triangular lattice. So here it is like, if you take three points, three nearest points, it forms an equilateral triangle. Now you choose one point in this lattice, and now how do you make a Wigner seed cell? The procedure to make the Wigner seed cell is, from this point which you have chosen as the origin, you join lines with the with all other points, all other lattice points. Then you take the perpendicular bisector of all these other lattice points. Okay. Now what will happen is, now you shade the region, or like choose that region which is nearer to the chosen lattice point. That will how do you do that? By taking this perpendicular bisector, and the region enclosed by this perpendicular bisectors will be your Wigner seed cell. So that's the that's the, in very simple terms, that's the region of your Wigner seed cell. Now this Wigner seed cell, why are we so obsessed about this Wigner seed cell, is that these are related to something called a Bragg plane and the Brillouin zone, Brillouin zone. So what is this Bragg plane? So remember that these lattices are drawn in 2 dimensions. So if you imagine this in 3 dimensions, then what would be it? Then the perpendicular bisector of the line joining these 2 points is actually a plane. Like, are you able to visualize that plane? Like, for example, this plane, it is coming out of this screen, and this plane. So whatever the line joining, their perpendicular bisector is coming out of the screen and going into the screen. That's fine, no?
Yeah, I'm still to visualize it, but yeah, I
Yeah,
can
I mean,
understand it is coming out of, yeah.
Yeah, you take 2, for example, if you, I don't know if you're able to see in the screen. So if you take 2 points, let's say the 2 ends of this pen are the 2, like, how do you make it? Like, for example, if you have this pen, and I want to find a perpendicular bisector to so this pen is your, that line joining the 2 lattice points, and you want a perpendicular bisector right in between. So that plane is what coming out of the screen. That is what I am saying. So if you take these 2 points, if you take these 2 points, then what is happening is the plane which is bisecting this is actually coming out of the plane. Okay, so that is the thing. So Brillouin zone is what the so now we are clear about what is the Wigner seed cell. Then the first Brillouin zone is the Wigner seed cell about a lattice point in the reciprocal space. So this Wigner seed cell, this, till now we are talking about this Wigner seed cell in the context of any given lattice. This can be a real lattice, or this can be a reciprocal, like this can be any given lattice. We are not specifying whether it is a real lattice or a reciprocal lattice. Now what we are going to do, now you take the reciprocal space, and in that reciprocal space, so for a given crystal we have a reciprocal space, and in that reciprocal space what we have is so that reciprocal space will be also a collection of some points. So you construct a Wigner seed cell about a lattice point in the reciprocal space. Then when we specify that it is the reciprocal space, we say that Wigner seed cell is your first Brillouin zone corresponding to that chosen lattice point. Okay, so this is the definition. For example, here it is the, let's say that this lattice corresponds to a reciprocal lattice of a given crystal, and we are choosing this point. Okay, so we could have chosen any point, we are just choosing this particular point. So this choice is totally arbitrary, we could have chosen any other point, but For now, let us say that we have chosen this one. So about this, now what we will do to construct the Wigner seed cell, we will take the perpendicular, we will draw lines to all the other lattice points, then take the perpendicular bisectors and see the region which is enclosed by those perpendicular bisector. That is your Wigner seed cell. Now since this is the Wigner seed cell of the reciprocal space lattice point, it is the first Brillouin zone for that crystal. Okay. Now these perpendicular bisectors to the line joining the origin of this reciprocal space to any reciprocal lattice point. For example, so this we have chosen as the origin. From here to this is another lattice point. So the line, the perpendicular bisector to the line joining these two lattice points is the plane perpendicular to this line. So that plane is called a Bragg plane. Okay. So what we have done, the exercise that we have done till now is we have identified a real lattice. Real lattice, it means like we have a real crystal. Then corresponding to that real lattice, we know the procedure to get the reciprocal lattice. So once we know the reciprocal lattice, we fix a particular lattice point as an origin and draw a line joining that origin to another reciprocal lattice point, and then take the perpendicular bisector of that line. So that is your Bragg plane. Now once we identify these Bragg planes, then we can identify what is the Wigner seed cell. That Wigner seed cell is our first Brillouin zone. So this is the procedure. So now, now you consider this. Here, the first Brillouin zone is the one which is enclosed by these Bragg planes, right? So when we are traveling around, if we traverse all the region without crossing any Bragg plane, that will be our first Brillouin zone. Now if we traverse in this lattice space such that only one lattice plane is only one Bragg plane is crossed, then we will be in the region of second Brillouin zone. Okay. So the region in reciprocal space that can be reached from the origin of the reciprocal space without crossing any Bragg plane, that is your first Brillouin zone. Similarly, the second Brillouin zone is defined as the region in reciprocal space that can be reached from the origin of the reciprocal space by crossing exactly one Bragg plane. Okay. Similarly, what we want to find as a second Brillouin zone, to find the second Brillouin zone, it is that region in the reciprocal space that can be reached from the origin of the reciprocal space by crossing exactly one Bragg plane. Okay. Similarly, you see this is second Brillouin zone, means one Bragg plane we have to cross. If it were a third Brillouin zone, then two Bragg planes we have to cross. Similarly, for nth Brillouin zone, it is that region in the reciprocal space that can be reached from the origin of reciprocal space by crossing n minus 1th Bragg plane, and exactly n minus 1 Bragg planes we have to cross, and not more or not less. So for example here, so this is an example of a square lattice we have taken. So let us identify what are our like first Brillouin zone and second Brillouin zone. So we have taken this point as our origin, and from here what we are going to do, we are trying to construct the Bragg planes. So how do we construct the Bragg plane? We draw the line to the other points. So for example, this is your first nearest neighbor. We take the perpendicular, we join the lines to the first nearest neighbor. So the atoms which are labeled in 1, they are your first nearest neighbor. Now you take the perpendicular bisector of these lines. If you take the perpendicular bisector of these lines, you get this plane. This is one Bragg plane, this is one Bragg plane, this is one Bragg plane, and this is one Bragg plane. So when you traverse this region without crossing any Bragg plane, you end up like shading this square region. that is your like the one which is shaded in green, that is your first Brillouin zone. Then if you want to now you we want to construct the other Bragg planes. So now how do you do? From origin you take the lines, you draw lines to the second nearest neighbors. So what I am tracing now in this laser pointer is your second nearest neighbor. Okay. Now you draw the perpendicular bisector of these lines. So this line, take the perpendicular bisector of that is going to be this. Okay. So now to reach the region which is in this yellow color, how do you reach? Like you start from the origin, you cross exactly one Bragg plane at this point, and then you reach here. Okay, if you go beyond this, then you have to cross this Bragg planes as well. Like but you have to cross only once. Like start from origin, you roam around, and if you cross the Bragg plane only once as you go away from the origin, that is your if you are crossing it only once, then it is your it is your second Brillouin zone. So if you are crossing the Brillouin zone, the Bragg planes nth time, then you will be at n plus 1th Brillouin zone. Okay, I hope this concept is clear. The one which is shaded in yellow, you have to cross this the Bragg plane at least Bragg plane once. Okay, so that is your second Brillouin zone. Similarly, you can get the third Brillouin zone. How do you get? You have to make the lines which are, we have to draw perpendicular lines from origin to the third nearest neighbors, then take the again perpendicularly bisect all these joining lines, and then take the region and close it and find. So after you have constructed these Bragg planes, start from the origin, go to those region in the space which is crossing the Bragg planes exactly exactly 2 times, then you will be in your third Brillouin zone. So that's how it is.
So we should visualize it in three-dimensional space, not in two-dimensional space.
Yeah. So for the sake of drawing, we are drawing in 2 dimension, but it is actually in 3 dimension. You have to visualize.
Yeah.
Okay. So we'll see an example if in 3 dimension very quickly. So what we have learned till now. So given a real space, we have a reciprocal space, and if someone gives us reciprocal space, we can get back the real space as well. Now once we have the reciprocal space, we know what is the Wigner-Seed cell of it, and the Wigner-Seed cell corresponding to the reciprocal space is called the first Brillouin zone. And we know what are the Bragg planes. Bragg planes are the perpendicular bisectors of the lines which are joining two reciprocal lattice points. And we know what are the Brillouin zones: the first Brillouin zone, second Brillouin zone, and third Brillouin zone. Okay, and these Bragg planes, these exist in the reciprocal space. Okay, this we just saw. Now what we are going to see in 3 dimension. So what we have seen up to 2 dimension, right? So you are able to see this video, right?
Yes. Yeah.
So
This is how we should visualize. Okay.
Yeah. Are you able to just hold on?
Truncated arc. Okay.
Okay. Are you able to identify what is this lattice structure?
Simple cubic, right?
Simple cubic, and there is one atom which is at the center of this cube.
Yeah.
So this is called a body-centered cubic.
Body centered. Yeah.
Yeah. So now how do you make the so this is a lattice. So given a lattice, we can construct the Wigner-Seed cell, irrespective of what is the whether it is a reciprocal or real lattice. Okay, Wigner-Seed cell is just so how do you construct it? You take this point, take the body center, and you draw lines to this all the neighboring lattice points. So which is shown here if you are able to follow this figure. So the body centered is somewhere inside, And what we have done is, we have taken the so what we have done is we have taken from that center, we have drawn the lines to all these corner lattice points and taken the perpendicular bisector of those lines. Are you able to visualize that lines? So what we are doing here
Yeah,
is,
I can see that. Yeah.
yeah, so let it here, like I hope it is like just here, if you can see. So what we have so there is a body center here, this is another body center, this is another body center, this is the corner of the same cube, this is the body center of the neighboring cube, body center of neighboring cube, and these are your, so what this plane is doing, this plane is your perpendicular bisector. So this is the
Yeah.
perpendicular, this plane is your perpendicular bisector, this plane is your perpendicular bisector. All these planes, these are your Bragg planes. Okay.
Okay.
And this particular structure that you get as a result of this like as a result of this is called truncated octahedron. Okay, so yeah, this is just the name of it. This is the or if someone asks you what is the Wigner seed cell of a body center cubic lattice, so you have to answer it is a truncated octahedron. Okay.
Okay.
So this particular structure, and see, this is characterized by hexagons. Hexagon is that Bragg plane. So the Bragg plane which is joining the body center to a corner, that is those will be hexagons. And the Bragg planes which is perpendicularly bisecting the line joining a body center to the nearest body center, that will be your this square. That is the square planes, the one which is squares. Okay, are you able to see?
Yeah.
So this square you get when, okay, I hope like, or you may take some time of your own at your own pace.
Bragg's plane, right? The plane.
Yeah,
The
this
square
is,
is.
this square is the plane. Like imagine this cube, it has a body center, and the cube neighboring it, that will also have a body center. Imagine a line joining
Yeah.
these two body centers and perpendicularly bisect it. So it will coincide with this particular plane.
Yeah.
Okay.
Which
So
will be
that's,
face centered.
huh?
Which will be like a face centered.
Yeah,
If you go with that.
yeah, but there is no face set and like this is parallel to this face of this cube. So the point to note here is that so this truncated octahedron is like, it is characterized by your hexagons and squares.
Okay.
Okay, and you can see that there would be like,
Typically, octahedron will have only um, uh, all the 8 sides of squares, but here it is hexagon and squares.
yeah, so okay, why it is called octahedron? If you imagine, if you like for example, if you imagine a square, you imagine a slice along the diagonal of this, so along the diagonal of this cube,
Yeah.
then how many, what would be the number of sides of that slice which is bisecting, which is intersecting with this structure?
1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8.
Yeah, you are able to see, right? Because like this hexagon is one, this
Yeah.
hexagon one, like here is a cube,
3,
and behind that there would be another
4.
hexagon.
Yeah. Yes.
Yeah, so there would be 8 of, so that is why it is called an octahedron, and it is like a truncated because it is like truncated here at, yeah, so
Yeah.
basically it is an octahedron, like you just have to, that's the nomenclature of it. Okay, so this is about the body centered cubic. Now let us go to another, this is called, this is the face centered cubic. Okay, in face centered cubic this is a bit tricky to visualize, so before going there, let us see this particular slide. So imagine that you have a, now it is a face centered cubic lattice. Okay, so here what we are doing is, so imagine that this is your cube. Your cube starts from here, from this point. So this what this particular square which I am tracing now is on the plane of this screen. Okay, and this cube then this is inside the screen, this particular, these atoms, this 1 2 3 4 that you see, 1 2 sorry 1 2 3 and 4, these 4 are inside that cube, and this is a face center on the plane of the screen. This is the face center of the cube which is perpendicular to the screen, and this is the face center which is like this is the face center which is on the top. You're able to see, right? Now what I want you to, like, this might be little difficult to imagine, but what I want to convey is that, so imagine that this particular, the one which I am shading now, that is on the plane of the screen. Okay, and this is so if it is on the plane of the screen, and this red one is coming out of the screen, but it is exactly, the distance is so how it is coming is like this. It is coming like this, and it is perpendicular to this and coming out of the screen. Okay, and this is going into the screen, and this is going towards the left side of the screen, and this is going towards the right side of the screen. So these are the 4 points. So you take a face center of the abscissa lattice, you have 4 of these points on top of it, like a fan. You are able to imagine this particular square, right?
Yeah.
Okay.
Yeah.
Now corresponding to this, so these points we are imagining that it is on the screen. Now you go down. Exactly on the plane of the screen. The one which is shown in the green here, it is into the screen, perpendicular, and which is coming out here, that is out of the screen and perpendicular. But it is coming exactly half the, like a by 2. If this is a,
Yeah.
if this is a,
Half the distance.
this is half the distance. This is a by 2, and this is a by 2. So you are able to see, right? These are the 4 nearest. So these are the 4 nearest lattice point, and so corresponding to this, you have 1 2 3 and 4. These red ones are coming out of the screen. This is also coming out of the screen. So okay, so you are able to see, on the bottom there are 4 lattice points, on the top there are 4 lattice points. Now let us see. So so like this much is clear, right, up to till now?
Yeah.
Yeah. Okay, now this thing is, so this is again we are taking as origin, and it is on the screen. Now you go left on the screen, and then go into the screen a by 2, by a distance a by 2. So you will reach this particular lattice points. Is this thing clear? Go to the left. So this is a face, right, which is perpendicular. This particular face is going into the screen, and since it is an abscissa lattice, it has a, so this particular atom is at the face center of the plane which is going into the screen. Is that clear, or like maybe you can think later? So similarly this so what I am drawing again here is, this one is the face center of the neighboring cube, and here also this is the face center of the neighboring cube, and this is the face center of another neighboring. So we can draw another, this is the face center of another neighboring cube. So these 4 are forming a plane. So how many So basically, this has four neighboring atoms, which is on this plane, on the plane which is, and four on the top, four on the down. Okay, so four on the top, four on the down, four on the plane of that point. So total 12. Now you take the 12 planes which are bisecting these lines. Okay. So when you do that, what you get is this kind of a structure. So you see, all these are rhombus. Are you able to follow, or a bit lost?
Yes, sir.
Yeah, no
little bit
problem.
lost,
So
but yeah.
okay. So maybe you can think in your free time. So the point to take away is that, so the resultant, so the procedure is same. The procedure, I hope you got in 2D at least, that you choose a point in the lattice, then you take to the neighboring atom or the neighboring lattice point, then take the perpendicular bisector of that line. Okay. Now what we want is to see what is the resultant structure that we get after we do all this thing. So what we get here is this kind of structure where we'll have 1, 2, 3, so this kind of rhombus, and there will be 12 of these faces, rhombic faces. Okay, so this is called a rhombic dodecahedron, which means 12 faced rhombus. So the Wigner seed cell of a face centered cubic structure is a rhombic dodecahedron. It is characterized by rhombus, and there will be 12 of these faces. This is clear? If you are not able to visualize, then that is also fine. You just have to remember this much information.
But why are we doing Wigner's itself? That's primary question.
Why are we doing?
Why are we doing Wigner's itself?
Wigner's itself. Oh yeah, that will come into. So we are going to talk about. So this like we'll see in a while.
What is that? See, my question is, like, we have Bragg plane, and we have, for simple cubic FCC, BCC, and all that. Then why we are talking about Wigner's itself? What is the advantage of it, or what is the benefit of this Wigner's?
Yeah, we are going to see that. So what was our idea? We have a reciprocal space. We are complicating our life a little bit more by saying that, okay, let us go to the reciprocal space. In the reciprocal space also, we are making such definition like, okay, Wigner's itself. We want to see the nature of the interaction with the lattice of any particular probe. That is what we want to finally achieve. But for that, we need to build up some background knowledge, and that Wigner seed cell is just like one of the concept that we will require. You will see in a while. Okay. At least you I hope you know how to construct that Wigner seed cell. Now.
Yes.
Yeah. So what we have till now is we have a material. Let us say that we have an abscissa lattice material. Okay. If the material has an abscissa lattice, its reciprocal space will have BCC lattice. This is clear. This we got from the last class. Okay.
Yes, last class, yeah.
And the Wigner seed cell corresponding to the BCC lattice is the truncated octahedron. Okay. So if your crystal is an abscissa lattice, then its Wigner seed cell will be a truncated octahedron. Okay. Similarly, if your real space is, or the crystal is your BCC lattice, then you will have a reciprocal space abscissa lattice, and the Wigner seed cell corresponding to abscissa lattice is your rhombic dodecahedron. Okay.
Okay.
So in reciprocal.
So what we were talking in our like previous two slides were starting from the reciprocal lattice space, not from the
here.
The pictures this one.
So
what we were
this is
drawing
just a
from the
lattice.
reciprocal lattice space.
So this we are not specifying anything what it is. We are saying that we have a lattice.
Okay.
Given
But
a lattice.
but if you see the explanation in the next slide that you showed, from a material with reciprocal BCC, you are talking about Wigner seed cells of truncated octet. So
Yeah,
if we start
see,
with the reciprocal lattice space of BCC only, you will see a truncated octet. Same thing, like reciprocal lattice of FCC only, you will see a rhombic octet. But originally, if the real space is BCC, then reciprocal will be FCC. So if it is, since you are saying that it doesn't matter whether real or this thing, reciprocal,
no, no, what,
if
see,
it is,
when we say that we have a lattice, we have, so lattice points, so these are lattice points here, okay. Here these are not the, so these are
yes,
lattice points. Now if in these
yes,
lattice points there are some atoms, if there are some
yeah,
atoms here placed at these locations, then we will say that okay, this is a real space lattice.
yeah,
Okay, now we are not specifying whether this contains this, what are these locations. This location can be the reciprocal space lattice points or the real space lattice points. When we say that it is a real space lattice points, these locations will have some so this will be the coordinates of some real atom. You're getting me? Like, that's the idea. So
yeah,
when I say a material with lattice points, then FCC lattice, then what I mean is the material consists of atoms which are so arranged that their location will make FCC configuration.
yeah,
Okay, and if you take the reciprocal of those lattice points, then you will get the points which are arranged in BCC. Now if you take this BCC lattice and construct a Wigner seed cell, then you will end up with a truncated octahedron.
yeah,
Okay, so that's the idea.
okay,
So what we have is, like, we have a real lattice. Real lattice means the lattice points corresponds to the location of atoms. From there we can construct a reciprocal lattice, and the Wigner seed cell in the reciprocal lattice is called the Brillouin zone, or it is spelled as Brillouin. It is like B R. Okay, so, and what are Bragg planes? Bragg planes are the Brillouin zone's boundaries, are called the Bragg planes. Because, like, initially we told that Brillouin zones is the Wigner seed cell. Brillouin zones are those region in space which can be reached by traversing certain number of Bragg planes. For example, nth Brillouin zone means we have to cross n-1 Bragg planes. So these Bragg planes, they constitute the boundaries of this Brillouin zone. Okay, for example, in this structure, these planes, the planes of this particular structure, that we will say that these are the Bragg planes. Okay,
yeah,
so that's the idea. So that's the definition. Now let us look at, so if you remember the last class, this was the evolved construction, and what we have told that, let us take two different points in the reciprocal lattice. What are the two? So here what we have done, this is a reciprocal lattice point. Okay, corresponding to that, if we are probing with certain wavelength lambda, and S vector is the so S is the direction of S is the direction, and you are sending some beam like this, and this is what you are detecting here. If you construct this, so this point and these points are what are these 2 points? These 2 points are the reciprocal lattice points. Now what is a Bragg plane? Bragg plane is a plane which is the perpendicular bisector of lines joining two reciprocal lattice points. So this is a line which is joining the reciprocal lattice point, and if you take a perpendicular bisector, then this is your plane. Okay, Now you see, in evolved construction, what we had? We had a sphere, and corresponding to this S vector. So S vector, what we do is, so this is actually S by lambda, S by lambda and S naught by lambda. Okay, so we are probing in this direction, and here we have a reciprocal lattice point, and then taking this as origin, we will make a sphere, and whatever the points which overlap with this particular sphere will constitute a point where this condition is satisfied. Okay, when this is the case, we say that we will have a diffraction. So that's where we get a diffraction signal.
What is the S here? Is S is the distance?
No, S is the
Lambda is the wavelength.
It is like 2 pi by lambda. It says you the direction. For example, so in real lattice, how you have to think? If this is your sample, this is your sample, this is your probe. This probe will have direction S, and so it will be like 2 pi by, is in one dimension, 2 pi by lambda and this x cap, let's say. So this is your S by lambda. So this S vector will tell you the direction and some factor. Okay, so this is how in real space, if here you are sending a beam and your and this is your this is S naught by lambda and this is S by lambda. Okay, so this beam you can think of it at like that. Okay, now what is, so in real space, here is your sample. Okay, just hold on. Let's say here is your sample, you are sending in light like this, you are detecting like this. So S minus S naught will be your this vector. Sorry, if these are in a triangle. Okay, perfect triangle. So this is S by lambda minus S naught by lambda. When this coincides with one of the HKL, this is what? This is a valid reciprocal lattice vector. Okay, so when it is a valid reciprocal lattice vector, diffraction will occur. Okay, so that's the idea. So this is just nothing but S by lambda is nothing but your wave vector. Now the point to note is that if you take the perpendicular bisector of this of the line joining these two reciprocal lattice points, you will see that this Bragg plane is intersecting this origin of this evolved sphere. Okay, so, and what that means is that this wave vector, it is like touching the so one end is touching the reciprocal lattice point, other end is touching the Bragg plane. So what we can say from here is that whenever the reciprocal lattice vector, so whenever the wave vector of the probe, that probe can be anything, it can be a light beam, electron beam, ion beam, anything. When you draw it such that one end is ending with one end is ending at the reciprocal lattice vector and the other is touching the Bragg plane, then diffraction will occur. Okay, so what we have is the diffraction will occur when one end of the wave vector of the probe, okay, it touches the Bragg plane. This is the key message of this particular slide. Like, I hope you understood.
So no, so those waves that satisfy this particular equation only can
undergo diffraction.
So basically, it is 2d sin theta equal to n lambda comes from this.
Yeah, so this is an equivalent representation of 2d sin theta equal to n lambda, the evolved construction.
Okay.
So this is the diffraction condition in the reciprocal space. In the real space, it is 2d sin theta equal to n lambda.
Okay.
Okay, and this HKL, it is related to like the family of planes.
Reciprocal,
Like
that's
you
correct.
can go through the last class, last to last class. So there we have talked about how this is related to the real space and all. Okay. Now in the reciprocal space, we got to know about. So now this is one of the advantage of coming to the reciprocal space. Now we know how the probe. So this is the information about the probe, and this is the information about the crystal. So, what is the condition that the probe should satisfy that it will interact with the crystal and give diffraction? So, the probe, so the question, the answer is diffraction will happen only when one end of the wave vector of that probe, it will touch the Bragg plane. What is Bragg plane? Bragg plane is the perpendicular bisector of the line joining two reciprocal lattice points. So we are
Yeah.
talking about reciprocal lattice points, means it is like an equivalent form of like uh, it has the information about the crystal of or of the material. Okay, so this tells you the condition between your probe wave vector and how your crystal should be such that diffraction will occur. Okay, so now let us try and do the example. So when a wave vector touches the Brillouin zone boundary, diffraction will occur. Brillouin zone boundary is what? It is a Bragg plane. This is clear, right? A Brillouin zone boundary is a Bragg plane.
Yeah.
Okay. So in the last class we have seen that this was the model of a metal we have talked about. So here the metal is not there. The extent of the metal is from metal or the crystal is from this particular point to this point, and it has a length L. This L is of the order of 1 meter, and it has the periodic lattice, and each of this well corresponds to an ionic core, and the effective length of this well is A. Okay, this is of the order of A. Okay, and corresponding to that there will be certain K values or the allowed wavelength. So K is nothing but your n pi over A. So K is n pi by A, for A is this distance. Okay, now we have also talked that this A is of the order of 1 nanometer and L is of the order of 1 meter. Okay, so the spacing between when it is n pi by A and n pi by L, and L is really very large as compared to A. If you compare these two, so here this K is very closely spaced as compared to this K. You're getting it right? So that's the idea here. And
Which case,
since
sir? Can you repeat this?
yeah, okay, sure. What we have is A is much smaller than L, because L is of the order of 1 meter and this is of the order of 10 to the power minus 9 meter. Okay, so A is very less than L. This is clear.
Yes.
So 2 pi by A, when this A goes to the denominator, is very large than 2 pi by L.
Yeah.
This is clear.
Yeah. So because A is very small.
Yeah, because A is very small. It is of the order of 10 to the power minus 9 meter. Now if you take a integral so n pi by A is what? Pi by A, 2 pi by A, 3 pi by A, and so on. Okay, so the gap between these two is really very large than this pi by L, 2 pi by L, 3 pi by L. So the gap between these two and gap between these two, which one will be more?
Which one, sir? Which gaps, sir? Two gaps. Pi by L, 2 pi by L.
Yeah, the gap between pi by A minus 2 pi by A is nothing but pi by A, right?
Yeah. Pi by A, 2 pi by A, that will be the big. big one.
Yeah, so this is really very very big, not only big. Okay, so
Yeah.
and energy we have is E equal to h bar square k square by 2m. So
Yeah.
h bar square by 2m k square is n square pi square by l square or a square, whatever it be it, based on what is the value of l. So now what we have is, if you try to plot this pi by a, so in the k space what we are trying to do, if you plot pi by a to minus pi by a, it looks like this. And this and here also, if you want to, so these points if you want to plot pi by l, 2 pi by l, so now you see that this pi by l is really very 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 small as compared to pi by a, isn't it?
Yes.
Yeah. Now what are we going to do? We want to find what is the value of energy of the nearly free electrons in the k space. So how we are going to do that? So E equal to h bar square k square by 2m, that we know.
Yeah.
So E equal to h bar square k square by 2m. Okay. And what we are more interested in is to see the behavior of nearly free electrons in the presence of lattice. So nearly free electrons will have energy level somewhere here, right? Okay. So it is enclosed in a length L, the nearly free electrons.
Yeah.
Okay. And what is this pi by a to 2 pi by a? These all denote. These denote. So if you have a 1D lattice, of, let's say, periodicity A, okay, then its reciprocal lattice will also be 1D with this gap as 2 pi by a.
Yeah.
Okay. This is your k space, this is your real space, and this is your k space. You are able to imagine this?
Yes.
If your lattice has a periodicity A, reciprocal lattice will have a one dimension, but periodicity is 2 pi by a. Now, since this is your k space, what would be your Bragg planes? Your Bragg planes will be, so that's what we have drawn here, 2 pi by a. That's what we have drawn here. So here is your reciprocal lattice point, reciprocal lattice point, reciprocal lattice point. Here is your reciprocal lattice point, reciprocal lattice point, and so on. Now and this is your one of the reciprocal lattice point which you have chosen as origin. Okay. Now you see, take two of this reciprocal lattice point and make a perpendicular bisector. So that will be in this pi by a, right? This pi by a, imagine a plane going into the screen. So that is your Bragg plane.
Yes.
Similarly, if you take, so when you have joined these 2 points, right? Now if you join this point with this point, 0 to 4 pi by a, then this is your another Bragg plane. This is your second Bragg plane, right? So to reach from here to here, you have to cross one Bragg plane, right? From origin, you want to travel from origin to here, you have to cross one Bragg plane. From here to here, if you want to come, you have to cross 2 Bragg planes. You are able to get this feeling, right? That
yes.
Okay. Now this is on the x-axis. What we have is the value of k. If you want to plot the for nearly free electrons, we have k equal to n pi by l, right?
Yes.
And if this we want to put in E equal to h bar square k square by 2m, what we will have is E is equal to h bar square by 2m. this is n square pi square over L square. Okay, but the see that this n pi by L is really very small as compared to this pi by
Smaller.
A.
Yeah.
So what we have
Yes.
is here very closely spaced. So this parabola that you see which I have drawn, it looks continuous, but it is actually what? It is actually
Discrete.
discrete. But it is so closely spaced that it looks continuous. Okay, this point is clear, no?
Yes.
Okay, now see, so this k corresponds to what? This k corresponds to the wave vector of the nearly free electrons. This point is clear. This k corresponds to nearly free electrons. This point is clear, no? Why? Because
Yes, sir.
these are your electron waves.
Yeah.
Now we have seen that whenever your probe, so okay, let us go to the next slide. So what we have is, so again just to recap what we have done. What we have done is, like, we have a metal of length L, and there are, so the periodicity is A. So this length is A, and it is of the order of the periodicity. So L is 1 meter and A is of the order of 1 nanometer. And for nearly free electron, the allowed k values are n pi by L, and for the bound electrons it is n pi by A. So what we have is, if it is totally free electron, then we have E equal to h bar square k square by 2m. If it is totally free electron, then k is continuous. Since k is continuous, we will have a parabola. But if it is nearly free electron, then it will look continuous, but it is not actually continuous. It is really very discrete. And if we look at only the bound electrons, or like the one corresponding to the lattice, then we will have very discrete points which are very separated. Okay, pi by A, 2 pi by A, these are the points, k points at your Brillouin zone boundaries or the Bragg planes. Okay, so what is our target? Why are we doing all this? So our target is to understand that how the interaction between the allowed values of k of nearly free electrons. What are these allowed values of k of nearly free electrons? Are this. Okay, so the electrons which are free, the nearly free electrons, will interact with the lattice. The periodicity of the lattice, how do you know? So if A is the lattice constant, 2 pi by A is the reciprocal space of that corresponding 1D lattice. How this will interact with the electrons which are nearly free? So these are the de Broglie. So this can correspond to the de Broglie wavelength of that nearly free electrons, and they will interact with the periodicity of the lattice. So now what we are going to see is how the electrons will see that periodic lattice. So that is the idea. So the reciprocal lattice stores the information about the periodicity of the lattice in reciprocal units. This point is clear. So if you have a real space in which the periodicity is A, the reciprocal lattice will have a periodicity of 1 by A, okay, or 2 pi by A, of the order of that. The k vector has the information of the allowed k and hence the energy, because E equal to h bar square k square by 2m. These values in the reciprocal space, and in the reciprocal space we have 2 pi by lambda. Okay, in k space we have looked at the Bragg planes, and the condition we have reached is that when the end of the wave vector touches a Bragg plane, diffraction will occur. Now let us consider a 1D lattice with interatomic spacing as A. Then the reciprocal space will be also having a spacing of 2 pi by A. So here these points 2 pi by a, 4 pi by a, 6 pi by a, this corresponds to the reciprocal lattice points. Okay. Now Bragg plane is the one, it is the plane which will bisect the line joining reciprocal lattice points. So from 0 to 2 pi, if you bisect, you get this red line. 0 to 4 pi, you will get this red line. 0 to 6 pi, you will get this red line, and so on. Okay. Now the thing is that whenever your electron wave vector, the electron wave vector is what? Electron wave vector is given by 2 pi by L, n pi by L. So whenever n pi by L is near 2 pi by A, so when this n pi by L touches a Bragg plane, then diffraction will occur. And when diffraction will occur, what will happen is that E equal to h bar square k square by 2m. So when diffraction will occur, then this this expression will get modified. This modified, and the point where the diffraction is happening, there you will not see this relation to be true. So what you get is, so you will start with a parabola. Remember that this parabola is actually discrete. But at the point where you are approaching the Bragg plane, that time your parabola will get distorted. So what you get is, this is the distorted parabola, and you get this kind of curve. Now you are able to see, right, why we talked about the Wigner seed cell? Because the boundary of the Wigner seed cell are the Bragg planes, and at that Bragg plane E equal to h bar square k square by 2m, that doesn't hold. Since it doesn't hold, it get modified, and there is a discontinuity in the energy of this, and there is a big discontinuity in the energy of the energy with respect to the k. So that is the reason we wanted to see the Bragg planes, because at the Bragg plane this diffraction occurs, and whenever diffraction occurs, the E equal to h bar square k square by 2m, that fades. Now you see, this leads us to the formation of bands. You see, from here, if you try to see, this corresponds to certain energy level. This energy level is here. Then the next, there is a discontinuity, and then the energy starts from a little higher value, and then it truncates at certain upper value. So here is another band. So corresponding to this thing, from this upper limit to this lower limit, you will have this band. So, and from this limit to this limit, you have another band, that is your fourth band. So this type of representations of the energy levels, this is called a flat band diagram, whereas this is called extended zone scheme. The relation between E and K, that is called an extended zone scheme. Okay. Now you see that here the choice of origin. So what we told that, okay, let us choose an origin in the reciprocal lattice, and then we will, with respect to that reciprocal lattice, we will find what are the other lattice points, and then take the perpendicular bisector. But the choice that, okay, this reciprocal lattice point is so this point is the origin, that choice is our choice. We could have very well chosen this point as the origin, or this point as the origin, or this point as the origin, right? So for example, let us say that, okay, let this point be the origin. If this had been the origin, what would be what your structure would have been? It would have been like this. Like, had this been the origin, it would have been like this, and like this, and so on. Okay, so what you have is, finally, for example, here you have chosen the origin to be this 2 pi by a, 4 pi by a, and so on. So So because our initial choice of the origin was arbitrary, so we could have very well chosen uh, other reciprocal lattice points as the origin. So here what you get is the energy versus k diagram. So instead of a parabola, so this is, instead of a parabola you got a distorted parabola. So this distorted parabola, when you translate, because you have chosen the origin very arbitrarily, when you translate you will get this kind of bands. So this is your first band, second band, third band and fourth band. Okay, since the choice of the origin is arbitrary, the and so we can shift this diagram by 2 pi by a. Okay, because our, so why 2 pi by a? Because our lattice spacing in the reciprocal space is a multiple of 2 pi by a. So when, yeah, you are saying something?
No, yeah, I was just listening.
Okay, yeah. So when you shift this diagram by 2 pi by a, and you keep translating and translating, what you will be ending up with is this. Okay, initially what we had? Initially we had this thing, no? Initially we had from here to here, then here to here, then here to here, here to here. So earlier that was the task. Here to here, here to here, here to here. Now when you shifted, you ended up with this like a sine curve kind of thing. So this is your repeated zone scheme. And what you see is that in the, so here what is the first Brillouin zone? The first, so these are your Bragg planes, no? Whatever is shown in the red, these are your Bragg planes. Okay, for example, the first Brillouin zone is from minus pi by a to the pi by a, because that is the region where you can traverse from origin without crossing any Bragg plane. So once you cross the Bragg plane on left hand side, you reach from this blue region to your green region. Okay, and here also, if you move towards the right and cross exactly one Bragg plane, you will reach to this green region. Okay, and if you want to travel and if you want to cross two Brillouin zones, so this is the first Bragg plane and the second Bragg plane, you are reaching in this pink region. This is your third Brillouin zone. Okay, so this is how it is. So this is your, and when, and in your second Brillouin zone, whatever the information is there, that can be equivalently represented in the first Brillouin zone only, but we just have to make a stacked plot. So this is called your reduced zone scheme. Okay, so this is about it. Your so reduced zone scheme is this particular diagram. Okay. Okay, now in 2 dimension. In 2 dimension, what we have is E equal to h bar square k square by 2m, and this k is actually kx square plus ky square, which is like n pi over ml, n pi over l. And what we have is this k spacings are also really very small. So these k's are actually discrete, but they are very closely spaced, like even in 2 dimension. So what we have is, if the number of free electrons are less, and so okay, just a moment. So this is your, like if you remember your this diagram, like recall this diagram. Okay, this one, the shaded green region is your first Brillouin zone, and these regions are your second Brillouin zone. Okay, now here what we see is, so here what we see is your, this is your first Brillouin zone, and this constitute your second, these 4 triangles constitute your second Brillouin zone. When you have less amount of electrons, then this circle, so this would be the circle, and the highest magnitude of k, that will correspond to your Fermi energy. You remember, right? The Fermi surface is the surface of the points of the highest energy electrons in that
Yes.
material.
Yep.
So if your electron levels are very very less, then they will simply be this sphere or this circular region. If you have little more nearly free electron, then it will still be a circular. Okay, but as soon as you have very large number of the electrons and you start filling it, and the wave vectors of these electrons will start to reach the Bragg plane. At the Bragg plane, diffraction will occur, and because of that diffraction you will have this distortion. Okay, so this is the general idea. So whenever your k vector of the electrons, they come near to the Bragg plane, diffraction will occur, and whenever diffraction occurs, there is a discontinuity of the energy. That discontinuity is called your band gap. Okay, so this is the
Yeah.
idea. So now we had seen that, for example, this is our second Brillouin zone, no? The second Brillouin zone, how it can be thought of as, so okay, and one more point to understand is that the area of nth Brillouin zone combinedly is same as the nth, is same as the area of the first Brillouin zone. How? You imagine this: you overlap this triangle and fold it onto the square along this curve. Similarly, fold this towards the left, fold this towards the left, and fold this towards the left. So the area of the Brillouin zone, second Brillouin zone, is same as the area of first Brillouin zone. Similarly, area of third Brillouin zone is same as the area of first Brillouin zone. And similarly, area of nth Brillouin zone, total area of nth Brillouin zone is same as the total area of the first Brillouin zone. So in second Brillouin zone, so that is what we had seen here also. If you see the first Brillouin zone, it goes from minus pi by a to pi by a. This blue region which is shaded. But the second Brillouin zone, it is like this and this. So when these green regions, if you take the length of this green region, it should be the same as the length of first region. Similarly, the third Brillouin zone, if you take the total length, it is same as the first. So that is the idea. So in the reduced zone scheme, where you take only where we overlap everything onto the first Brillouin zone, this looks like this. Okay, so that's all to it. Let us discuss some question answer based on these discussions. Okay, so what is Wigner? So can you answer the first question?
Weakness is a region space that is dashed to a given lattice point, then to any other lattice point with respect to lattice point closest, right? Closest.
Yeah. What else?
I don't know whether it can nearest also you can say. Or?
Yeah, it is the same thing, no? Closest and nearest.
Yeah.
Yeah.
I was not sure why they had to. Yeah.
Yeah, it is just
Dependent is not the right way, right? Dependent or farthest.
Dependent is not. It is closest and nearest. These are the two correct options. Okay. Okay. What about the second question?
Is the dashed bisector to the perpendicular bisector to the joint on the reciprocal.
Perpendicular bisector.
To
Correct.
any.
What about the third question?
Can be defined stated as it is the first Wigner cell. That is correct.
Correct.
Reciprocal lattice point and reciprocal region any. Yeah, that is also before any Bragg plane in any direction.
Yeah, perfect.
Region in space that can be reached from without crossing, that is not correct.
Region in space that can be reached from origin without crossing.
Without crossing will not be there. We have to cross anyway, Bragg plane, right?
So this is the first Brillouin zone.
Yeah. Okay, without. Okay.
So for example,
First
if we have
Brillouin
this lattice, so how do we construct the first Brillouin zone? To construct the first Brillouin zone, we have to take the perpendicular. You have to take this join to the nearest atoms, and then take the perpendicular bisector. Take the perpendicular bisector of this, perpendicular bisector of this line, perpendicular bisector of this line, perpendicular bisector of this line. Now you have to set those area which you can travel without crossing any Bragg plane. These are the four Bragg planes, Now from this is you have chosen as origin. Now you go across all the regions without crossing any of the bragg plane. If you don't cross any of the bragg plane, you will basically end up covering all this square region, isn't it? This is your
Yeah.
first Brillouin zone.
Yeah.
So your
So okay.
first
So third is also correct.
third
Third
is
is also
correct.
correct. Only
Fourth you
fourth is
read.
not correct because first brilliant zone we cannot cross second bragg zone, right?
Yeah, that is true. But what it is saying?
Subset of the region enclosed by the second bragg plane
Yeah. Second
in
bragg
all
plane would
directions.
be what? Second bragg plane will be here. You join this line here. Join join this line here. Join this line here and take the perpendicular bisector. Join this line here. Take the perpendicular bisector. This is your second bragg plane, and this
Yeah.
is the subset of the first bragg plane. So this is also correct.
That is also true. Okay.
Got it right?
Yeah.
Yeah. Okay. What about this fourth question?
Reduced zone scheme is based on dash brilliant zone. It is actually nth brilliant zone. First, second, third, fourth, everything is right, right?
First, second. Just hold on.
Reduced zone
No,
scheme.
reduced zone scheme. You is what? Reduced zone scheme is our this, no?
Only one brilliant zone, correct? Yeah, it is
Yeah. So this is our reduced zone scheme, and this is the first Brillouin zone.
minus per base. That is first, yeah, first zone.
Yeah. Yeah. Correct. Okay. What about the fifth one?
First, what is it? Whenever diffraction condition is satisfied or diffraction occurs, certain values of energies are discontinuous.
Discontinued. Yeah. And
Allowed, is it?
no. How is it allowed? You see here what is happening. Certain values of energy are so earlier these values of energy were there. Now these values of energy are
Yeah.
forbidden, isn't it? Like for example here,
Yeah.
these values of energy are not there. These values of energy are not there. These are forbidden now,
Yeah.
right? So it
Okay.
is forbidden.
Discontinuous and forbidden, no? Okay.
Yeah.
So we don't say existing.
No, it is not no more existing. No,
Okay.
like you understood. No, why we take that one?
Yeah, yeah, yeah. Got it. Yeah.
Hmm.
So that zone is not allowed to calculate energies because we have moved the
Like
origin from by 2 pi by a.
certain value of energies are discontinued. Okay, this discontinuous. It sounds. I'm not so sure what this means actually, but forbidden is
Yeah,
for
it is
sure.
supposed to be discrete. It is supposed to be discrete. Yeah.
Yeah, forbidden is correct. That is for sure. Okay.
Discontinuous is what they want to say. It is basically UOUS. So
Okay.
basically it is discrete. That's the meaning, I think.
Okay, maybe we'll go with forbidden. Okay. That was what it the like sometimes NPTEL questions it is like for
Yeah,
example
it's
this
confused.
little
Actually, in
bit
the previous thing also I had some doubts. Yeah.
yeah. And we'll go to the next thing. But you know the concept, right? So the main concept is this: you have certain energy values which are forbidden. Okay. Okay. Now what we have is okay. Next question will go. This question.
2D lattice. Witness cell will be a
Yeah, here
four-sided.
here we need to
Four-sided
do a
figure.
bit of work because we are going to look for a 2D Wigner seed cell will be dash-shaded figure for a 2D lattice other than square and rectangular lattices. So let us draw. Why it is not coming? Okay. So let us draw a lattice which is not other than square and rectangular, means a triangular lattice it can be, or it need not be a triangular lattice also, it can be some oblique lattice as well. But if you go with oblique lattice you will get the same result, so we'll just draw a kind of triangular lattice only. other than rectangular and square. That is the condition it is. So anything will give you a correct result. Now from here, can you see how do I draw the Wigner seed cell? I choose a origin. Let me say that okay, I will take one of these lattice points as an origin. Let us say that this is my origin. From this origin, I will join lines to the all the other points.
Yeah.
Then what I will do, then I will take the perpendicular bisector of all these lines. So perpendicular bisector of this line will be this particular line. This is the perpendicular bisector of this line. Perpendicular bisector
Yes.
of this one will be this. Perpendicular bisector of this line will be this and this and which one? Yeah, and this and this. And now I think we are almost done with all the perpendicular bisectors. So what is the region that we got? The region that we got is this region, from here to here to here to here to here to here. So what we have here is a hexagon.
5 sides. 5.
5.
6 sides, huh?
Yeah, 6 sides. So this has 6 sides. So answer is 6.
Other than square and
Yeah.
rectangular
So
lattice.
if you
So
had
you're not choosing a. If you put a square lattice, it will change, right?
yeah, for square lattice it is a square, no? For example, if you have this, how what you will get? You have to you choose this as origin. Draw this this, and now you choose make the perpendicular bisectors. Perpendicular
It will be 4
bisector of
lines.
yeah, this perpendicular bisector of this line is this. So perpendicular bisector of this is this. You're able to see, no, what is happening?
Yeah.
So what is the structure that you are getting in case of square? It is again a square.
Yeah.
Okay, so that is the thing. Okay, so second question.
The first brilliant zone is a dash about a lattice in a
A dash about a lattice point in reciprocal space.
reciprocal space. It's a Wigner's size cell.
Yeah, correct. Okay, what is the next question? This is second question. Third question. The difference between first brilliant
First
zone
brilliant zone
and
different between third brilliant zone in terms of uh, how do I say that?
yes, see,
Total area,
one thing,
overall shape. Yeah.
one thing I just like, maybe I don't know if I told you or not. If you look at these things, for example, here you see that second brilliant zone is this yellow region, right?
Yes.
The total area of the yellow region is same as the total green region.
Yes. Yeah. Area is same.
Yeah, so if you fold these triangles onto this square, you'll exactly find the overlap,
Correct.
right? So that is the thing. So similarly, if I had drawn the third one, and there would the total area of those, but the third one would have been like some so some triangle here, so it would have been a bit different, like for example a triangle here, 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 here. So the shape would be different, but and the shape would be like more numerous, but when you add
Yeah.
the total area, it will be same as the first Brillouin zone. That thing is there. Okay.
Yeah.
So that's what we saw here. The first Brillouin zone is 2 pi by a. Second Brillouin zone is this green region and this green region. The total length is of the second Brillouin zone
Same.
is same as the first.
Yeah.
Similarly for the third, if you add this and this, it will same as the first. Similarly for the fourth, and like nth Brillouin zone is same, has same area as the first Brillouin zone. Okay, so now you answer this question.
So total area, no, not total area. Overall overall shape of individual pieces which are different. Yeah, shape of individual pieces which are spread out across the space. That will be the one
Yeah,
answer.
that is different. Yeah, this is the correct answer.
Nature of its boundaries.
The boundaries are all the Bragg planes only, no? So that is not
Yes.
okay.
Overall shape is
Overall
also
shape it
different,
will
right?
be like
Area is same, but
yeah. The overall shape, I think what they mean is when you collect them together, what you will get. You can overlap them onto a square. But this is for sure. It is true that mm, the shape of individual species which are spread out across the space, that will be for sure it is different.
yeah.
Okay.
Okay, sir.
I mean, yeah, I can understand that this is a bit vague, like what they mean by
Yeah, yeah.
overall shape. Okay, but so you have to go with this. But I hope you understood the concept, irrespective of like
Concept. Yeah,
clarity
yeah,
of this
yeah.
question. Yeah.
Got it, sir. If you go to that picture, sir, the 33 picture that you
So
made, the 33, not this, you showed a picture for that first and second relay zone image, right? I think in the class notes.
this one.
Not in
Or
the any previous one. You drew it, the image.
this one.
Yes, this one, the green 8. Yes. Here, if I talk about this, the green region has basically, can I say, like, fragmented into like this many, brilliant, fragmented into this many pieces. Can we say that
Yeah,
the green
you
region
can
is fragmented?
think of it as okay. This triangle you see, right? Uh, how do I say?
I can see 2,
This
3,
triangle
4, 5, 6.
can be overlapped into this triangle.
Yes.
Like for example, let me just I have we have this
So
diagram.
only when we take the first brilliant zone,
Yeah, I'll just show you in
how
just a
many
minute.
fragmentation we have?
Yeah, just hold on. We have this diagram, no? This diagram we
Yeah.
just drew. So
Yeah.
so this diagram I'm drawing again. What I was going to show here, you have this. This is your first Brillouin zone.
Yes.
This you can think of it as this. Now
Two
you
triangles.
you
Oh,
take this region, this triangle, and invert it on this side. Invert it on this side like this. That is your
yeah.
second Brillouin zone. Now you take this
Yeah.
triangle and invert it on this side. This is your the second triangle of that Brillouin zone. So this area is same as
Yes.
this, right? These two area.
Yes.
Now you take
Mirror
this
image.
area and this. So this is to show that the total area of the second Brillouin zone is same as the total area of the first Brillouin zone.
No, when we fragment it, when we fragment the first brilliant zone, how many fragments we can see?
No, we so it doesn't make sense to fragment. So that fragment is just for our visualization. That
Yeah, when we
the
visualize, how many fragments can we visualize in this
it,
first
it,
space?
it can be like it depends on what is the number of fragments you want to do. Like for example, here we have shown into 4 fragments because we want to make an equivalence of area of these 4 triangles. Suppose if we have a third, so the third one it looks somewhat like this. The third Brillouin zone,
Yeah,
it looks somewhat like this.
which is like 8 fragments, correct?
It will have 8 fragments. So the number of fragments actually increases as you increase the number of Brillouin zones. Okay, so this is your third. Now to
Yeah.
understand that these 8 actually has the same area as the central square, so so there is a way to fragment this square into these 8 triangles. Okay, there is a way to do that. Now again, if you look at the fourth Brillouin zone, the fourth Brillouin zone will be something like this, like this, like this, like I mean, this might not be the exact accurate one, but the number of fragments that you can think of it is just for a visualization tool to show that nth Brillouin zone has the same area as the first Brillouin zone.
Okay, sir.
Yeah.
And one more thing, basically, the first Brillouin zone in a body center, you told that in a body centered cubic, it will be rhombic uh,
Body center cube, yeah, that is
decohedron.
the Wigner seed cell, yeah. But in three
Yeah.
dimension
So
it is.
so first Brillouin zone will be a Wigner cell of a body centered will be a Wigner cell of a face centered, or it will be Wigner cell of a body center only.
Can you
First
please repeat
Brillouin
that
zone.
again? What you were saying?
First Brillouin zone
First Brillouin
of
zone
a body centered
of a body center.
will be Wigner cell of the face centered or body centered only.
So what is the body center? It is a real space crystal. So what is it talking about? Like which you are talking about some question or just in general doubt?
General, you told one information like if you told me to remember that body centered will be having a octorhombohedron, right? Octorhombohedron.
Just hold on. This question. I mean, sorry, not question.
Yeah,
See,
Wigner cell of a face centered cubic rhombic decohedron. Yes.
so but this
What
is
is the Wigner cell here? Will it will be a BCC or a FCC?
Wigner seed cell. Wigner seed cell is not BCC or FCC. Your lattice is
No, but
BCC or
that is
FCC.
Wigner. Yeah, but your if you see that it says what is your first see Wigner cell of a face centered cubic system.
Yeah.
So it will have a below like um, brilliant zone of face centered only or body
No,
centered.
no, see, no. Like I think you are getting a bit same. So
No,
when
when
we
we
talk
connect
about,
this to the
yeah, just hold on. Like when we talk about Wigner seed cell, it has no. So a Wigner seed cell is just a mathematical construction. It is geometrical construction. It has no physical meaning, no Brillouin zone, nothing.
okay.
You got it right. So Wigner seed cell is
Yes.
just a geometrical construction which is done by the method that we had discussed. Okay, that point is clear, right?
Yes.
If you are
So
given
Wigner cell can brilliant zone can be anything,
No,
any type.
Brillouin zone cannot be anything. Say, Wigner seed cell, it has no physical significance. It is just a geometrical construction. If your lattice
Okay.
is your face-centered cubic lattice,
Hmm.
then your if your lattice is your face-centered cubic lattice, am I saying correct? Yeah. If your lattice is face-centered cubic, then your Wigner seed cell will be a geometrical figure which is called rhombic dodecahedron. Now, when we talk
Yeah.
about a Brillouin zone, so Brillouin zone, it has a physical significance because it tells you about diffraction and other interactions. Okay, so
Yes.
Brillouin zone, the first Brillouin zone is the, and like you try to like focus what I'm saying. Wigner seed cell. So Wigner seed cell of the reciprocal lattice is your Brillouin zone. So when we
Yeah.
say the Wigner seed cell, it doesn't matter. It is just a geometrical construction. But when your
Okay.
lattice is your reciprocal lattice, and then you take a Wigner seed cell in that reciprocal lattice, then it is called a Brillouin zone. Is that clear?
Got it, sir. So bodies. So for body centered, it is which shape, sir?
So what is body center you are talking about? Your lattice is
When we
body
say
center,
body,
or crystal is body center, or reciprocal space is body center?
crystal is body centered.
See, if your crystal is body center and you want to find what you want to know, you want to know the Brillouin zone shape.
First brilliant. Yes.
Yeah, if your crystal is okay, let me just go with like this. This we discussed. Okay, suppose you are saying that crystal is body center, right?
Yeah.
What you want to know? You want to know shape of
Brilliant.
shape of Brillouin zone you want to know. Okay. So what is the Brillouin zone? Definition of the Brillouin zone. First Brillouin zone is, tell me what is the definition?
two reciprocal points perpendicular to the
No, it is
like
the, like in terms of Wigner seed cell, it is the
okay.
Wigner seed cell of what? Cell of reciprocal reciprocal lattice point.
Okay. So then for BCC, reciprocal lattice pointer is FCC, right?
Yeah. So now you, yeah, if your crystal is BCC, then what is your reciprocal lattice? Your reciprocal lattice is FCC,
FCC.
and for FCC, what? Reciprocal lattice is FCC. Now for FCC, what is your, so this is because crystal is FCC BCC, reciprocal lattice is FCC. Now what is your Wigner seed cell of FCC? It is rhombic
Rhombic octahedron.
dodecahedron. Okay.
Dodecahedron.
Now since this is your shape, the shape of Wigner seed cell is this. You understood the flow of argument?
Yes, got it, sir.
Yeah.
Rhombic octahedron. That's the shape of it. Okay. So going to that slide you had put on the discrete energy, right?
Discrete energy.
The last slide.
This
Yes.
one?
Previous one. Previous one.
Yeah.
Yeah, here. See, 2 pi by A is our
Reciprocal
basically
lattice
the,
point.
yes. Or can we call it as 0 to pi by A as a Brillouin zone?
0 to pi by A as?
Brillouin zone?
It is a part of Brillouin zone, no? See? What is the first, what is your Brillouin zone? The first Brillouin zone is minus pi by A to pi by A. 0 to pi by
basically 2
A,
pi by A.
it lies under the first Brillouin zone. It is like a subset of that.
So in this, for example, when you show this pi by A and 3 pi by A as red, right?
Yeah.
Those are all allowed black planes or
So those are your Bragg planes. No, like why I have shown this in red, because there is no lattice point there. These are your Bragg planes, and this point is so this is where your Bragg plane is intersecting with the line joining. So what are your lattice? The 0, 2 pi by A, 4 pi by A, 6 pi by A. That's where your reciprocal lattice points are there. Now if you bisect from 0 to 2 pi by A, that line, if you bisect that, you will get this pi by A. So this plane you will get. If you bisect the line joining 0 to 4 pi by A, then you will get this lattice, this Bragg plane.
Okay.
So this 2 pi by A is also a bisecting point and also a lattice
Bragg
point.
plane.
Yeah, and also, yeah. So you got that right.
In the previous slide and this slide, the energy bands both point to the same forbidden bands or same like here. See, you see the bands here marked as blue.
Yeah.
They are forbidden bands, right?
No,
Forbidden
these
bands.
bands are allowed bands, because this is where your energy is there.
Okay.
So this corresponds to this top. So this one corresponds.
So the gap is the forbidden band. The gap.
Is the forbidden gap. Yeah.
Okay. Okay. So gap is my forbidden gap.
Yeah.
And that was my Bragg planes. Okay, sir. Yeah, clear.
Yeah. Okay. Now we go to the next question. Is this true?
Which one, sir? A Brillouin zone is always consistent. False.
Yeah.
This
Why
can be
false?
discrete.
Yeah.
It's a discrete.
It is discrete.
Packet. Yeah. It's a discrete packets of pi by L.
Perfect. Yeah. Oh, this is always continuous. False.
False.
Yeah. Perfect. What about this?
HKL. Diffraction phenomenon occurs when S by lambda minus S naught by lambda is equal to HKL whenever K is equal to S by lambda. Wave vector touches bragg plane. Wave vector touches bragg plane. That is correct.
This is correct.
And wave vector touches brilliant zone boundaries. That is same as bragg
This is the
planes.
same, yeah.
One end of wave vector touches evolved sphere. What is evolved sphere, sir? I forgot.
So evolved sphere is this one, no? Like this we had drawn. This is a reciprocal lattice point, and so we draw a sphere. Oh, sorry, this is not a good sphere, but yeah. So we have this sphere. Sorry, yeah, you understand that this is a sphere.
Yes.
So
Yeah.
so here, like if you have another, okay, where it went. Okay, anyway. So if you have another reciprocal lattice point, this is S by lambda, and this is S naught by lambda, S by lambda, and if your S by lambda, if any of the reciprocal lattice points falls on this sphere, and then this vector is HKL, because HKL is what? HKL is your reciprocal lattice vector. So when
Yes.
S naught by lambda minus S by lambda uh, falls on this thing, this what? This sphere, then diffraction happens.
So this is also correct.
This is correct. So that is the starting point, right? That we took as.
Okay, that is also the answer, is it? I thought that is part of the question.
No,
Okay.
yeah. So one end
So,
of
and so one end of the wave vector touches, that is also correct.
yeah, that is correct because it is touching, no? Yeah, that is correct. What about this?
1D lattice. If we have lattice points at every 2 by A position,
Yeah.
A is the lattice spacing in real space. Every n pi by A where n is an integer. What is that? What will be Bragg's plane? Yeah, every n pi by, that is correct. N pi by 2A or n pi by A? It is n pi by
Every n pi by a. What will the Bragg plane's
n pi by
position
A.
for 1D lattice? If we have a lattice points at every 2 pi by a position. See, lattice point.
Yeah, it is n pi by A, right?
Yeah, lattice point at 2 pi by a position is n pi by a. Yeah, correct. Because you have to bisect, no? When you bisect is n pi by
Yes.
a. And
N
it
pi
is
by
the,
A.
you see this point, all lattice.
Center position between the lattice points and the lattice points.
Yeah, center position between the lattice point and the lattice point itself. Yeah, perfect. Yeah. What about
All the lattice points is not right?
yeah, all the lattice points, why not right? Because the origin lattice point that you are not considering.
Correct.
Yeah. Okay, cool. We'll go to the next question now. What about this?
Yeah, this is what I was trying to understand now, I think. Yeah. Okay, so what are we asking is
What
what
is
is are the information that can be extracted? We have forbidden bands, that is what I just now told.
see reciprocal
But,
lattice point positions? Okay.
Yes.
Can it be extracted from here?
Yes.
Yes. Why? Because these are your reciprocal lattice point positions,
Yes.
isn't it?
Yes. Energy of wave vector you can find. Allowed and find.
Energy of
forbidden
wave
where
vector
can
that you can
find.
find, because this is the diagram about energy. Sorry, energy is not energy, and this is your K. Energy
Okay,
you
yeah,
have.
wave vector.
Energy of a wave vector is given any, yeah, reciprocal lattice point position also, you know. Allowed and
Allowed and
forbidden
forbidden
band gap
That
values.
is also given.
Allowed
That is
values
given.
is these are your allowed values of energy, and these are your forbidden energies.
Forbidden.
That also you
Yes.
can know. Position where
Positions
diffraction
where
condition is
diffraction
satisfied. Where it is satisfied.
That is also there.
It
That
is
is also Bragg's
satisfied
plane.
at this Bragg planes. That is also there.
Yes.
Then what about this?
M. What will happen if we plot them on the same scale length? Bound electron zone of length M.
See, let us assume a material of length L has a bound electron zone of length M.
You just drew a diagram, no, last time. That
Yeah.
I think that is
What will
is
happen when you plot
tutorial.
both them on the same scale length? See, the energy levels of the free electrons are more closely spaced than that of bound electrons. Is this not true?
That is not right.
Why? The energy levels of the free electrons. See, Free electrons means what? They are more free, they have more larger
Free
area to
to,
move
yeah,
around.
yeah.
And
But
when
will it be
we
closely spaced?
see the energy levels is what? E equal to h bar square pi square
H
over
cross K,
2
yeah,
m, and this is n pi by L square.
yeah.
These are for free electrons. L
Yes,
is really large. For bound
yes.
electrons, it is h bar square pi square by 2 m n pi by A whole square. In this case,
A is too big.
A is
A is
m.
too big.
See, m is too small
A is,
because it is like A is too big for free electrons,
yes,
and for this is for the bound electrons.
yes.
You got
Okay.
it right?
Yes. So
So the
free
first,
electrons are more closely
so
placed.
this is
Yeah.
correct. What
Bound
about the
electrons
second
are more
question?
closely.
Energy
Not
levels
that
are
is not right because
not
bound
right.
electrons are more.
Yeah.
Yeah. Energy
And
levels of the free electrons are higher in energy than those of the bound electrons. That is true.
that is true.
Energy levels of the bound electrons
Yeah,
are higher in energy. That is not true.
that is
Yeah.
correct. Perfect. Yeah, you just have to remember this diagram. If you, I hope you remember the diagram. Like,
Yes. Yeah.
yeah. So there's,
Dash represents details of the E versus K relationship at all energies in billion zones at each lattice point.
huh.
All energies in billion zones at each lattice point. So it is basically reduced zone scheme
Yeah,
at E versus K, repeated zone scheme,
yeah.
flat band diagram.
No,
Extended zone scheme also is correct.
yeah, because this reduced zone scheme, extended and repeated, these three are equivalent only. But
Yeah, same, similar.
in flat band, you don't have the idea about. So, for example, see here. So here this is a flat band scheme. Here you don't have what is the energy, what is the x-axis, you don't know,
Correct.
right?
So
So,
that is not there.
huh?
That is not there.
So this is not the
Flat band
correct.
is not.
See, flat
Okay.
band scheme, you don't have the idea about what is your k values. On the x-axis, it is not k.
Okay.
You see here, here x-axis, it is usually the position actually. You don't have
Okay.
the value of k.
K is not available. Okay.
Yeah, k is just here in the reduced zone scheme,
Energy.
repeated, and these are equivalent things. Okay, cool. Now let us go to the next question. A slice of Wigner seed cell
Yes,
passing through the body center and parallel to 100 plane of a body centered cubic lattice is slice of Wigner seed cell.
Yeah. Passing through the body center
Yeah.
and parallel to 100
So
plane.
it is a body center,
So
okay? Body centered
HK plane is
cubic
given.
means it is what? It is truncated octahedron.
Octahedron, yeah.
If you remember our
But
discussion, then
Wigner cell will be for FCC, which is a
no. Here it is not saying anything about the crystal, no, or Brillouin zone.
okay.
It is not
Okay,
saying
it is
anything
only
about that. You don't have to. You just have to think of the lattice. So the lattice is
okay.
your,
There is no reciprocal space here.
yeah, lattice is your body centered cubic, and you want to find. So this is your body center. This point. Uh,
Yeah.
Parallel to 100 plane. So 100 plane means what? 100 means it is just
X-axis is 1,
x-axis
0
is
is Y.
1. So there is one like this, like this. X-axis is 1, and
Y is 0, Z is 0. HKL, it is basically HKL plane, right?
yeah,
HKL
yeah.
100.
So 100 is a plane which you have to slice through this, like center from the center, like in half you have to cut through the body center. It has to
Yeah.
pass a plane which is parallel to the x-axis. You got it right?
Yes.
Like a plane which is perpendicular to the x-axis. Rather. So if this is x-axis, you have to cut it through the body center like this, and you have to think of a
Yeah.
plane which is Like let us go to this truncated dodecahedron. Here, what you have to do is just come here and go to here and control V. You see, you have to like cut it through this cube along this line, along this line. Sorry, cut here, cut here. Then from here, then what you will get is, so if you cut along this line, this plane, you are able to visualize, right? Then what you will get is one,
Yes.
two, three, four. Like you will get like 8 of those. Uh,
8 of them. Yes.
yeah. So
So
that,
octahedron.
so it will be your octahedron. Okay. So that's all for today.
Sir, one more. Yeah, I think. Did I ask you all the questions? I think I had something. Okay, yeah, we asked that clearly. Yeah. Okay, sir.
Yeah.
Thank you, sir.
Okay.
It's really